Okay, we're going to go ahead and pick up where we left off in class on Wednesday or on Friday, depending on if you have me during second or fifth period. So we're going to move or continue working with the same example, but looking at it a little bit differently. So directions here say now let's attempt to find the exact area under the curve y is equal to x squared from x is equal to 0 to x is equal to 1. So if you guys remember back in class, we used the Riemann sum, so the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum, as well as the trapezoidal approximation to get estimates for the area underneath that curve between x is equal to 0 and x is equal to 1. This time we want to find the exact area. Okay, so what we're going to do is we're going to take the interval from 0 to 1 and divide it up into n subintervals. So we're going to let n equal the number of subintervals. And then if I want the base length for the Riemann sum to be uniform, we're going to say that that base then is going to be equal to, again, we said that that was going to be equal to the length of our interval, which in this case is 1 minus 0. And then we're going to divide that by the number of rectangles that we're going to use in our approximation, which in this case is going to be n. Okay, so our uniform base length for all of the rectangles is going to be 1 over n. Okay, and our height is going to be equal to like our function values at wherever we are taking the rightmost endpoint, because we're going to do a right Riemann sum for this. Okay, so r sub n is going to be equal to, since that base length is uniform, I'm going to go ahead and pull or factor that base length out. Okay, and then if we take the interval from 0 to 1 and divide it up into n subintervals, that next value on the number line is going to be 1 over n, then 2 over n, and then so on and so forth. So with our right Riemann sum, we're going to be taking our heights from the rightmost endpoint of each subinterval. Okay, so it's going to be the function value at that rightmost endpoint. So on the first interval from 0 to 1 over n, we're going to be taking our height from the function value at 1 over n. On the next interval from 1 over n to 2 over n, we're going to be taking our height from the function value at 2 over n. Next one's going to be taken from the function value at 3 over n. And we keep going until we get to our last rightmost endpoint, which is 1, but I'm going to go ahead and rewrite that as n over n, okay, which is equivalent to 1. Okay, so if we want the function values at those inputs, we're going to take those inputs and then plug them into the function x squared. Okay, so that first value then is going to be 1 over n quantity squared. The next height is going to be 2 over n quantity squared. Next one is 3 over n quantity squared. And we keep going until we get to the last one, which is n over n quantity squared. Okay, so I want to rewrite each of those expressions then inside the brackets. So we get r sub n equal to 1 over n times, I'm going to apply the square to the factors in both the numerator and denominator. So we get 1 squared over n squared plus 2 squared over n squared plus 3 squared over n squared plus all the way out to n squared over n squared. And when I look at each of those fractions inside of the brackets, they have that denominator of n squared in common. So I'm going to go ahead and factor 1 over n squared out from all of those quantities. So when I do so, when I pull that factor of 1 over n squared out front, when I multiply it by 1 over n, that gives me 1 over n cubed. And then the quantity we're left with inside of the brackets is 1 squared plus 2 squared plus 3 squared plus all the way out to n squared. Okay, now in algebra 2, and I know we don't cover this at our school just for lack of time, but there is something called proof by math induction that can allow you to actually prove that this statement here in the brackets, you can, using proof by math induction, show that if you take 1 squared plus 2 squared plus 3 squared plus all the way out to n squared, you can mathematically prove that that expression is going to be equal to n times n plus 1 times 2n plus 1 all over 6. Again, I don't expect you to like know that. I had to look that up myself because it's not something that we work with routinely in math. Okay, so once we have that, then I can go ahead and multiply those two expressions together. So we get n times n plus 1 times 2n plus 1 all over 6n cubed. Okay, now once I've gotten here, we said last time the more rectangles we use in our approximation, the more accurate our approximation becomes. And I said that if we use infinitely many rectangles, that is going to wind up giving us the exact area under our graph. So if we take the limit as n goes to infinity of this right Riemann sum, okay, which is going to be the limit as n goes to infinity of n times n plus 1 times 2n plus 1 all over 6n cubed, then that's going to give me the exact area underneath that curve from x is equal to 0 to x is equal to 1. Well, as n gets large, the end behavior of that numerator is going to be the term of highest degree, which is going to be 2n cubed. The end behavior of the denominator is 6n cubed, and 2n cubed over 6n cubed winds up becoming 1 over 3. So that limit there is equal to 1 over 3, which tells us the exact area under that curve. Now, is that the most efficient way to do this? No. Like we're going to learn when we get into chapter 5, and I'll probably show it to you in a few seconds in today's lesson, a faster, easier, more efficient way for us to compute the actual area under a curve. Okay, so I want to look at this statement next. Okay, so if we want to calculate the area under a curve, the area A of a region that lies under the graph of y is equal to f of x, where f of x is a continuous function and lies above the x-axis, is the limit of Riemann sums of the areas of the rectangles. Okay, so we're going to kind of like take what we did in that example above, and then we're going to like generalize that statement. So when we take the limit as n goes to infinity of r sub n, okay, so we're taking some interval and we're going to break it up into infinitely many subintervals. Well, if I do a right Riemann sum, if I started that Riemann sum at x sub 0 and finished it at x sub n, then for a right Riemann sum, the rightmost endpoint of that first subinterval is going to be x sub 1. The rightmost endpoint of the next subinterval is going to be x sub 2. And then we're going to call the distance in between the two subintervals, we're going to call that delta x. Okay, so if we're doing a right Riemann sum, like the base length is uniform throughout, so that's why we factored this delta x out. And then we're going to be taking our height from the rightmost endpoint of each subinterval. Okay, so I'm taking my first height from the rightmost endpoint of the first subinterval, which is going to be the function value at x sub 1. I'm doing my second one from the rightmost endpoint of the next subinterval, which is going to be the function value at x sub 2. And I keep going until I get to the rightmost endpoint of the last subinterval, which is the function value at x sub n. And what we can do is we can take this limit expression here, and we can write that limit expression in summation notation. So we're taking the limit as n goes to infinity of the sum from I is equal to 1 to infinity of the function value at x sub I, which is the height of our rectangles, times delta x, which is our base length. And what we can do with this limit is we can take this limit right here, and mathematically in calculus, this is how we define something called a definite integral. And again, we're going to talk more about definite integrals as we move through the next section and the sections beyond in chapter 5. Okay, now similarly, I can write up like a similar limit definition for a left Riemann sum. Okay, so the exact area under the curve I can say is equal to the limit as n goes to infinity of the left Riemann sum. Now, it's going to be a little bit different for the left Riemann sum. We're still starting at x sub 0, and then the endpoint of that first subinterval is going to be at x sub 1. The endpoint of the next one is going to be at x sub 2. Our last one is going to be x sub n, but the one that precedes it is going to be x sub n minus 1. Okay, again, the distance in between the two endpoints is going to be delta x. Okay, so that distance is uniform. That's why we factored out delta x here. And then that's going to be our base length, our uniform base length. And then our heights are going to be taken from the function value at the leftmost endpoint. So on the first interval from x sub 0 to x sub 1, the leftmost endpoint is x sub 0 of the first subinterval, so that's why we're taking the function value at x sub 0. On the next subinterval from x sub 1 to x sub 2, we're taking our height from the leftmost endpoint, which is the function value at x sub 1. And we keep going until we get to our last subinterval, which is this one here. We're going to be taking our height from the leftmost endpoint, which is the function value at x sub n minus 1. And again, we can take that statement and write it in summation notation as well. The sum is going to look a little bit different because this time we're starting the sum at I is equal to 0, and we're ending the sum at n minus 1. But again, the function that we're plugging that into is still f of x sub I. Again, that's our heights, and then we're going to be multiplying that by delta x, which is the length of our base. And we can say that that statement, so this one here, in summation notation, that is also equal to the integral from a to b of f of x, which we are integrating with respect to x. Now, a faster way for us to do this. So let's take the same thing that we did up above. So we want to calculate the area under the graph of x squared between 0 and 1. So again, in math, this is what we call a definite integral. And we're going to talk about what that means in the next section, really in the next two sections. So the way that we do this in calculus is if that function is continuous on the interval from 0 to 1, which it is, the way we mathematically do this is we're going to take the antiderivative of this function, which the antiderivative is going to be x cubed over 3. I know we add c whenever we take an antiderivative, but we don't do that in this particular instance, okay? And then we're going to evaluate that antiderivative at the two endpoints of our interval. Okay, so when we evaluate that at 1, we get 1/3 minus, and then we're going to evaluate that antiderivative at the starting point, which is 0. So 0 cubed over 3 is going to be 0, and that winds up giving us the exact area under a curve. Way more efficient than what we did up here. Okay, so again, that's going to be the technique that we use going forward. Okay, so I'm going to do another example similar to the previous one that we looked at. And then I have some examples of utilizing data table information as well with the same concept. Okay, so directions here say to approximate the area under the curve f of x is equal to x squared. So we're taking the same function, f of x is equal to x squared, from x is equal to 0, from x is equal to 2 to x is equal to 5, using, in part A, a left Riemann sum with 4 subintervals, in part B, a right Riemann sum with 4 subintervals, for part C, a midpoint Riemann sum with 4 subintervals, and for part D, a trapezoidal approximation with 4 subintervals. Okay, so here's what I want you guys to do. You guys are going to go ahead and pause the video, work this through. The values get a lot messier with this one, so I'm going to go ahead and let you use your calculator for this, and then I want you to round the final result to 3 decimal places. Okay, whenever you're done with that, go ahead and unpause the video, and then you can check to see if you work things through properly. Okay, so working this out, our base for our Riemann sums and our height for our trapezoidal approximation, if I want that distance to be uniform, I'm going to go ahead and take the length of my interval, which is the ending point, minus the starting point, over the number of subintervals that we're going to use, which in this case is going to be 4, and that winds up becoming 3/4. So I'm not going to graph this, but if I were to look at the subintervals, we would start at 2. Our next one would be 2 plus 3/4, which is 8/4 plus 3/4, which is 11/4. Next one would be 11/4 plus 3/4, which is 14/4. I'm not going to simplify that because when I plug into the function, I want my denominators to be the same. Next one will be 14/4 plus 3/4, which is 17/4. And the last one is 17/4 plus 3/4, which is 20/4, which is equal to 5. Okay, so that's how you would break up the interval from 2 to 5 into the 4 equal subintervals. Okay, so if we want to calculate L of 4, I can pull the base length out front. So that's 3/4. And then we're going to multiply that by the sums of the heights. So for the left Riemann sum, we're taking our heights from our leftmost endpoint of each subinterval. So the first one will be f's value at 2. Second one will be f's value at 11/4. Next one will be f's value at 14/4. Last one will be f's value at 17/4. Okay, and then when you use your calculator to approximate that, I got that to be 31.406. Okay, when we do the same thing for R of 4, again, our base length is uniform. I'm going to pull it out front. And then this time I'm going to be taking my heights from the function values at the rightmost endpoint. So the first one will be f's value at 11/4. Next one will be f's value at 14/4. Third one will be f's value at 17/4. And the last one will be f's value at 5. All right, so when we approximate that, I got that to be approximately 47.156. For the midpoint Riemann sum, we are going to be taking our heights from the midpoint of each subinterval. Okay, so if I want to calculate the midpoint of the first subinterval, it will be the sum of those two. So 11 over 4 plus 2, which is 8 over 4. That becomes 19 over 4, and then we divide that by 2. So that first midpoint is going to occur at 19 over 8. So I'm going to take the base length, pull it out front, and then my first height will be the function value at 19 over 8. Again, as we mentioned in class, the distance in between the two midpoints is going to be the length of our subinterval. Okay, so I'm going to add 3 over 4, which is like adding 6 over 8 to the previous midpoint to get the next midpoint. So when I add 6 over 8 to 19 over 8, we get f of 25 over 8 as our height for our next subinterval. When we do it for the next one, we get f of 31 over 8. And the last one is going to be f of 37 over 8. Okay, so when we approximate that, we get 38.859. And then when we do the trapezoidal approximation, I know I mentioned in class last time we can take the average of the left and right Riemann sums. And that's probably the fastest way to do it here, but I want to work on setting this up as well. Okay, so the trapezoidal approximation is going to be 1/2 the height. So our height is uniform. We're going to go ahead and pull that height out front. And then we're going to multiply that by our bases. Now, again, with the trapezoidal approximation, we use the first base once. We're going to use the interior bases twice. So it's going to be f of 2 plus 2 times f of 11 over 4 plus 2 times f of 14 over 4 plus 2 times f of 17 over 4, and then we use the last base once, okay, plus f of 5, and then when you evaluate that and approximate that on your calculator, we get 39.281. And we said, again, that the midpoint Riemann sum and the trapezoidal approximation are going to be the best estimates. We look at those, I think, like a good guess for the exact area under the curve is going to be 39, and that's actually what that exact area is going to wind up being. Okay, so we'll go ahead and finish off this lesson in the next video.